degraded, has been remodeled, there are these little holes in it, microscopic, you can't really see it, called Halschipp's lacunae. And that's how you know bone's being remodeled. You get this little indentation. So you build on one side, and the osteoblasts come from mesenchyme. And what we're talking about is ectomesenchyme. You know? Yeah, you know. Osteoclasts don't come from mesenchyme. They come from blood-forming cells. And they're multinucleated and they're huge cells. So they're easy to recognize. Oh, compact bone. How do you grow compact bone? Well, there's several types. One is circumferential that goes around the long bone. And then there's internally, you have what are called Haverian system or osteonic systems, which are these little guys, little tubes. And inside of the tubes is a vascular system, as well as a nerve. That's what keeps it alive. Now this is kind of important because bones are living. And once that osteoblast is trapped and it mineralizes around itself, those are they form osteomes. Those are those tubes. And that's an Haversian system, the blood system that runs in the middle of the tube, and then connecting those are Volkmann's vessels that connect those tubes in a perpendicular sense. The whole thing here is, when we start talking about enamel is dead. That's why when you damage enamel, it's over. You can't do anything. Dentin is not. Dentin is more like bone. So dentin actually has a blood supply. And as I told you, it's got a wicked nerve supply too. But it has a blood supply, so you can create dentin even late in life. It's called tertiary dentin. But in bone, you can create bone. But enamel, dead. Once it's formed, that's the end of it. Which is too bad. If you're a shark, you just make more teeth. This is just the same thing. There's a Haversian system. The circumferential bone is the stuff out here that runs around the outside. Then you get these tubes called osteomes. And on the outside is the periosteum. That's a tubercular bone. Endosteum would line that stuff in there. I figure most of you guys probably had some of this, right? That's what an osteome looks like. You can see that it's formed these little tubes. It mineralizes as it works its way out, and that's where the osteocyte lives, the bone cell itself. And this is what that Haversian system looks like, or osteome looks like. And it's kind of neat because it's like plywood. It changes, each one of those little layers changes the direction of the collagen, which makes it particularly strong. And it can resist shear. And you can also age your bone because they remodel. You have primary osteomes, secondary osteomes, and tertiary osteomes. And as you get older, you remodel these things. So if you count osteomes, you can kind of guess how old the person is. Not really, kind of 10 years either way. Which is, I don't know. Did any of you ever take archaeology? I'm not an archaeologist, I'm a paleontologist, but anyway. Archaeologists have this, if you ever read their reports, if it's a kid, they say, oh, you can tell from the teeth or the bones, you can age it, this 6 or 8 year old, okay. And if it's a really old person, they just say it's, senile, old. But everybody from the age of 20 to the age of 60, when you read archaeological reports, they always say, 35, 40, because they can't tell. Can't tell how old the person is. Now we can, if you got teeth and you look at dentin actually lays down at a regulated pace and you can say something. But days of rule don't do that. Formation of bone, osteogenesis, ossification, mineralizing of bone. Endochondral, this is what we have a cartilaginous bottle. And as I said, I don't want to confuse you, but it also is intramembranous too. Endochondral, it does have a cartilaginous model, but it also lays bone underneath the periostome. So that's kind of a shaky way to divide it. But basically, a long bone is endochondral from the neck down, except there's a couple membranous bones that aren't in our head. Clavicle. Clavicle used to be a head bone, and so it's also membranous, and parts of your scapula too. And this is just how it ossifies. You know, you have a cartilaginous model, then you have a foramen, you develop a foramen there, you start to ossify in the middle, you build a diaphysis like that, then you build a secondary center here and another secondary center there, and that's how you can create a bone that has a complex joint and also can elongate the bone. This is just another shot of that. This is a real, these things, you know, it's called an epiphysis if it has a joint attached to it. If it does not have a joint attached to it, it's called an apophysis. Now, why am I telling you this? Because there's all sorts of apophyses in the human body that when you're young, you can, all that attaches to it is a muscle, like the lesser trochanter on your femur. And I bring this up because when we have anybody here that was a sprinter in high school, when you come out of the block, what kicks your leg forward, like that, is a part of your, it's part of your quadricep. It's rectus femoris. And rectus femoris crosses the hip and attaches onto the lesser trochanter. And I can't, happens, it's a big thing. You kick that leg forward and that muscle just pops that apophysis off, and that's a real problem in sprinters. You can always tell when your friend's on the ground writhing in pain. That's not an issue. You can also pop the thing off your calcaneus too. Your Achilles tendon can pull it off. It's another battle. All right, intramembranous, you don't have a cartilaginous model. You have a membrane, and you start ossification within the membrane. You know, and it expands out. In fact, you normally have several different areas of ossification. It expands out till they touch each other. But that's how you make the plates, like your parietal bone and your frontal bone. And keep in mind, in your skull, all these bones that are doing this, they're all ectomesenchyme. Same old story. And this is the cartilaginous interface. This would be the physis, that cartilaginous pad. What happens is you start ossifying, you turn them into tubes, what are called cartilaginous tubes, and then you ossify those tubes, and that's how the bone grows in this direction. So you get ossification following these, the cartilage dies, and then you build more cartilage on top, but that's how you make the bone longer. So there's a constant, you're laying down cartilage, at the same time you're ossifying it, and that's how you're getting a longer bone. If you hurt yourself and shear off one of these, and this is a real problem in children, if you knock it hard, it'll fuse. And once it fuses, then you're in trouble because the bone can't grow anymore. So that's why it's some kids have one leg that is significantly shorter than another, one arm that's shorter than another, because they knocked off the epiphysis. They can now go in and kind of, they can cut through it and hope it'll grow, but it's kind of iffy. This just shows the growth plates in a kid. You see that? That's an epiphysis right there of the radius. There's the radial diaphysis. That's the metaphysis. And that's the physis, that line right there. So here's an adult and you don't see it because it's fused. And all of you, I should think that most of your bones are fused. That's another way you can, if you go into orthodontics, and I presume some of you are planning to do that, it's a real problem trying to figure out when you want to do the treatment. If you do it too early, then what happens is the mandible and maxilla continue to grow and it screws up everything you did. If you do it too late, it's hard to do. So you want to try to figure out where the kid is in the growth series. Still, the best way to do it is looking at the wrist. But they've stopped taking x-rays of people's wrists now, although they still do it here, I know, and they still do it, because you can tell where someone is in the growth series by looking at the ossification of the wrist. Or their foot, it's just easier to do the wrist. Bone remodeling, okay, it's, deposition, osteoclast, they grow it. Resorption, osteoclast, they take it away. And it really should not be called bone remodeling. In the beginning, it should be called bone modeling, because you're building the bone. Later on, you remodel it, if you have to. But it's semantics. This is what, I told you, vitamin D, very, very important, because you can't get calcium to cross your gut if you don't have vitamin D. Parathyroid hormone, that's another one, controls blood calcium. Calcitonin drops the calcium in your blood. So you've got all these things in your endocrine system that are there to control bone growth. Wait a minute, you don't get to leave. No, he cleared it with me, it's okay. I just wanted to scare you. Okay, osteoclast. No, he came to me and said, excuse me if I have to leave. Osteoclast, yeah, we already know this. Remember, osteocytes, the bone cells, are transformed into osteoblasts when they get trapped in their matrix. So they get stuck in there and they can't get out. And that's why you can't have interstitial bone growth. It has to be appositional. That's an osteoclast. It's multinucleated. They're huge, big cells. They create that lacuna, that house-shaped lacuna, and they eat the bone away. And then over here you've got osteoblasts that are building it. And I think I've got a cutting cone here. Yes, I do. Cutting and filling cone. You're going to have to know this, not necessarily for this class, but you're going to have to know it later when you take, with Mark Hines, with bone growth, facial growth. This is a big one, because obviously your face changes enormously from being a 1-year-old or 1 day old to being an adult. And it strangely continues to change even after that. And then part of the mechanism that allows this is this cutting and filling cone. And all that means is that you've got, running on the outside here to remodel the bone, you have osteoclasts. And they go in, and that's why they call it a cone. They go in and they remove them. Then coming behind them are osteoblasts that then lay down bone in a different fashion. And that's how your face can grow in this dimension and in that dimension. And because you're constantly having to take the bone and add bone and remove it and add bone and remove it and add bone and then remove it, so you can keep, otherwise you look like Quasimodo. So it's important that you're able to do that. So that's the cutting and filling cone. And then finally, this is a bone fracture. This is the woven bone. When you break a bone, this is why they set bones, incidentally, but this is nature's way of trying to do it. When you break a bone, you end up with that high protein, well vascularized, low mineralized bone, and disorganized. If you look at it under a microscope, it just has little organization. And it tries to hold the two pieces of joining one another. Because if you don't do that, you will create what's called a pseudoarthrosis, a pseudo joint. If you have bones that aren't properly set, then what happens is they go back and forth, and the body thinks it's a joint, and they make a fake joint. It doesn't work very well, but that's what it tries to do. So the woven bone is what holds it together. And as I told you, woven bone is the same as alveolar bone. It's in your mandible and your maxilla. Only woven bone will naturally, in and of itself, remodel and turn into cortical bone. So if you broke a bone 10 years ago and you look at an x-ray today, you probably can't even see the collar of woven bone is gone. It's remodeled away. Funny thing about alveolar bone is it doesn't do that. It stays in that almost embryonic sort of a condition. Oh, there's Mr. Shark. We'll see this next time. The reason I show sharks is they have we have something called a dental lamina, and that's what forms your teeth. We'll talk about that in excess next week. But ours, you get two sets of teeth, right? You get your deciduous set, and then you get your adult set. Why do you have deciduous teeth in the first place? You couldn't get it through the birth canal. You gotta have little tiny faces because our brains got too big. So you want to have those, and you wear them out, you get rid of them, you get your adult teeth. And when your first adult molar comes in, at about age 6, that's when your brain stops growing. In all mammals. Don't you think that's cool? I don't know why. I have no idea why. But that holds true. So a 6-year-old, 7-year-old human, their brain's not growing any bigger. That's about as big as it's going to get. Which is why they look like aliens anyway. Because their face still has to grow, but they got really big heads. Never noticed that, did you? Of course you noticed that. But you know what? See, we're all programmed to go, oh, they look like puppies. It's true. It's true. If you got big eyes and little face and little chins and a big head, that's a puppy. You go, oh, look at the puppy. Oh, look at the kitty. Oh, it's true. You know it's true. Well, the same thing. We're hardwired to like babies too. Find them cute. Well, anyway, Mr. Shark, he maintains a permanent dental lamina. So he sheds teeth like crazy, breaking teeth all the time, but he just creates new teeth. Why don't we do that? I know you guys would be out of a job. Fortunately, we don't for you. You can, but you're here to save us. That's an important thing, because our enamel's only meant to last, the whole human body is only meant to last 50. I know, I hate to say that. It kills me to say that. It's only meant to, after 50, like you're living on borrowed time. And how do I know that? Because of menopause. Once you stop reproducing, you know what? Mother Nature says, goodbye, you're off the radar screen. It doesn't matter anymore. Kind of scary. Trust me, you hit 50 and stuff breaks. It's no fun. Hyaline cartilage, it's good for 50. All right. That's where we get our teeth. Scales. That's it. I will see you next week. Go home and celebrate finishing your exam.